Hello friends, so today we are going to learn about breadth first search. This has to be one of the most popular coding pattern out there, and in my opinion this coding pattern has to be asked in probably millions of interviews all across world, and there is a very simple reason for that. Breadth first search solves some of the most common real life problems that we see in our day-to-day life, and using this technique there are actually bunch of different really popular products and companies are completely built upon. So that is why interviewers love asking breadth first search type of questions. Second thing is that breadth first search is also referred as BFS, and throughout this problem we would be interchanging between the names of breadth first search or BFS. Now the flow of this video is going to be that first we are going to have an overview of what this breadth first search technique is, and in this overview we will also see that what type of data structures use this breadth first search technique. Next we are going to see that what does a typical workflow looks like for any single breadth first search problem. In the end we are going to see three different real life examples, and these examples that I have chosen, they are really popular example, plus they solve some real life scenario or some real life problem. And I'm going to explain you the problem statement. I'm also going to explain you the different solutions, and I'm also going to show you the Java code for all of the solutions that I'm going to explain. So this is going to be really action packed video in my opinion. This is going to be much more informative compared to my other coding pattern videos, because this coding pattern in itself is so much more popular. So I highly encourage you to pay some extra attention and learn this technique as efficiently as possible, because this can have tremendous rewards for you. Now, if we want to see the overview of breadth first search, basically we have to understand that where breadth first search technique applies. It typically applies amongst two ways. First one is a tree data structure and second one is a graph data structure. And the way we can use this breadth first search technique in tree or graph data structure is that breadth first search is basically a mechanism to traverse over or to go over all the nodes in the breadth for in any given tree or graph data structure. That is it. That is the whole point of having a breadth first search, that this technique allows you to iterate over any single tree or any single graph, but in that iteration you would be able to find some meaningful value that, and you would be able to solve the problem that you are actually aspiring to solve. So first let's see the overview and the typical flow of breadth first search. For that I'm going to use one tree and one graph example. So first I have decided to show you the BFS on a given tree. Now in this example we are using a binary tree. So what binary tree means is that every single node has at most two children, nothing more than that. They can have less than two children, but they cannot have more than two children. Now I mentioned that BFS is simply a way to traverse over the given tree, and the logic we are going to apply is that because this is a tree, we are going to start iterating from the root node, and in the root node first we will visit the root node, then we would visit the children of the root node before visiting the grandchildren of this root node. So we are going to visit children first, then for those children again we are going to visit their children first, and even for those children we are going to visit their children first. So every single time we are iterating level by level inside any given breadth first search for a tree traversal. Again let me repeat that we are going to iterate in terms of level. So first we are going to iterate over the level 0. In the first iteration we are at the root position. So I already mentioned that the path is going to look like this, that first we visit value number A, then we are going to visit its children. So currently the children are B and C. So then we are going to visit nodes B and C after visiting node A. From this B and C, for B currently we have the children D and E, so that we are going to visit after visiting C. So for B we are going to visit children D, and also we are going to visit children E. Again for C it has children F and G. So again from E we are going to visit to node F, and then we are going to visit node G. In the end for this particular E, it has also a child called H that we are going to visit in the last. And if you notice that first we visited the first level that only had one node, second level had two nodes, third level had four nodes. So we visited all four nodes, and in the end we visited the last level, and that is where the position H is located. Now you must be wondering that how we have been able to achieve this. Well, I will explain you that how any typical computer is going to do this, but first let's see an example for a graph as well. So let me quickly draw a graph and we will see a BFS example, and then we will see that how to implement it like a typical common workflow for a BFS. Okay, now for this example, we would see that how a BFS is going to work for a given graph. Now, unlike tree, graph does not have a root node, which means we can start our BFS from any single node. And again, just like tree, the logic we are going to use is that inside the tree, we were actually iterating the children of the any given node before visiting its grandchildren. Well, in the graph, we don't have a children, but we actually have neighbors. So again, we are going to apply the same logic that we are going to iterate the neighbor of any particular node before iterating their neighbors. So again, we are going to go level by level in this fashion. This is just for an example purposes. But there is one key thing that we have to take care in graph that we were not concerned about in a tree. So I'm going to explain that in the example. Suppose we start our traversal from this value number 3. Okay. We can take any arbitrary value. I'm just taking 3 for an example. So first node we are visiting is going to be node number 3. Now we are going to visit the children of this 3. So children of this 3 is 5 and 4. So we are going to visit node number 5 and node number 4. We can visit this in any order. There is no particular way, but just for simplicity, I'm just going to write down one of the possible path. Now for this 5, there are no children or no neighbor. So because 5 does not have any neighbors, we would not need to iterate over any further, but this 4 already has some neighbor. So now from this position number 4, okay, first neighbor is 6 and second neighbor is 2. So we are going to visit 6 and 2. Again, 6 does not have any neighbor, so we are not concerned about this one. But for this 2, it has 2 neighbors, 1 and 0. So again, let's try to do this. So 2 visits node 1 and again node 0. Now what would happen at this position node 1? How many neighbors does 1 have? Well, 1 also has 2 neighbors. First one is node number 2 and second one is node number 0. So again, if I try to visit the neighbors of 1, what is going to happen is that I'm going to visit node 0 and also node 2. But now what happened is that from this 2, we visiting after visiting multiple elements, we came back at the same position. So again, from the 0, rather than creating a new loop to 1, we can actually create a new loop to 2 over here, which means we are actually running in circles because there exists a loop in this case. And remember, trees cannot have loops, but graphs can have loops, and that causes a big problem here. So whenever we are dealing with graphs, we will always have to make sure that we find a way to keep track of all the nodes that we have visited already. And in order to keep track of visited nodes, typically a hash set is a great example. And most of the time, whenever you are dealing with a graph problem, and either you are using breadth first search, so this is one of the most popular technique. Another technique is a depth first search that I'm going to explain in the future videos. But in either cases, you have to make sure that you take care of the visited node, because you do not want to end up in an infinite loop cycle. So now again, let's just go back and let's just mark all the nodes that we have visited. So 3 we already visited, same way we visited 5 and 4 and 6 and 2. So all of these nodes we have visited so far, and now let's repeat the same process. So from this 2, we have the 2 neighbors, 1 and 0. So 1 and 0 are the neighbors. And remember, all the nodes that I just mentioned that we have visited, we are going to put them in a hash set. Okay. So hash set would be able to quickly tell us whether any node has been visited or not, because it operates in big O of 1 time complexity in order to find whether any element exists inside the hash set or not. And that is why it is a great way to use visited hash set. Now again, coming back to our BFS pattern. So from this 1, we have 2 more possibilities, 0 and 2, but 2 is already visited inside the hash set, so we are not going to visit 2. And 0 we already visited. Now 1 has also been visited. Now from the 0, we only have 2 neighbors, 2 and 1, but since both are visited, we cannot go further anywhere, and we can determine that we have actually reached to the end of our traversal for our graph. And this is how the breadth first search is going to work inside a graph. Now you understand that how does a typical flow works, but can you explain that how we would be able to actually implement this breadth first search? What is the technique we are going to use? You already know that this can be used in a tree, a graph kind of a problem, but we need some way to keep track of all the nodes. So one way, we are entering the current node that we are going through in the BFS, and we will also have to keep track of its neighbors inside graph. So the best way to use a BFS is that we can actually implement it using a queue. And what this queue is going to allow us is that it is going to allow us to keep track of all the neighbors of any particular root item, because they would be still placed in a queue. And remember, queue has a wonderful property, and that is that first in, first out. So the first children that came in would be the first children coming out, and if they also have subsequent children or neighbor, they would still be inside the queue. Now let me give you a quick demo on how a queue would work, and we are going to use the same example. So let me clean this up a bit. So for the same example, as mentioned, we are going to use a queue. And inside the queue, what we are going to do is, first imagine we are starting our iteration from value number 3. So we are going to populate the queue with value number 3. Now our BFS function is going to do two things. First thing it is going to do is check that whether queue has any element or not. Queue has element 3. So now we have this value number 3 that we haven't taken care of. And also remember, we are also going to use a hash set that is a given fact. Okay. So for all the values that we have already visited, I'm just going to mark them in this graph. Now, first thing we are going to do is, for this value number 3, we are going to check that whether 3 has any neighbors or not. And 3 does have 2 neighbors. So first neighbor is this value number 5, and second neighbor is value number 4. So the moment we identify the existing neighbor for any element, we are going to add them to our queue. So awesome. Let's just add them, 4 and 5. And also at the same time, we are going to check inside the hash set. So since they were not visited, that is why I added them in the queue. Okay. So first we would check whether they exist in the hash set. If they don't exist, then we add them to the queue. Now we have visited all the neighbors of the value number 3. There are no other neighbors that exist. So we can mark 3 as visited. The moment we mark 3 as visited, we are going to also pop it out of the queue. So now our queue is only going to have 2 elements, and that is 4 and 5. Now 3 has already been taken care of, and 3 was one of the first elements that we visited. Okay. Now next we are going to check whether queue has any element or not. Queue has element number 4. So again we are going to repeat the same process. Does 4 have any neighbors? So 4 has 2 neighbors. First neighbor is 6, second neighbor is 3. But we check in the hash set, 3 is already visited, so we do not visit 3 again. But 6 has not been visited, so we will add entry 6 over here. Again we repeat the same thing. We pop 4 out and we move all the values. Okay, so currently again values that are there are 5 and 6. And also I forgot that 4 also has the neighbor 2. So apart from 6, 2 is also one of the neighbors, and after that we would pop 4 out, and from 3 we would visit value number 4. Okay. Again we repeat the same thing for 5. 5 does not have any neighbors, which means we can pop 5 out, mark it as visited, and we be done with it. Same we are going to do with 6. Okay, so after 3, 4 we are going to visit 5 and 6, and they are all visited, and we are going to dequeue them as well. So currently inside our queue, the only value we are going to have is going to be value number 2. For this value number 2, first, okay, neighbor 4 already visited, no need to visit. Neighbor 1 not visited, so add it over here. Neighbor 0 not visited, so add it over here. After visiting all the nodes, remove 2. So 2 has been removed. Okay, awesome. Now 2 has been added over here, and then again repeat the same process and also mark 2 as visited. Again repeat the same process for 1 and 0. So since 1 has neighbor 0, so we are going to add 0 over here. And also at the same time we are going to check the hash set. Hash set already has 0, so we would not add it over here. My mistake. But we would not add, and then we would dequeue 1, and then in the end we would dequeue 0. So simply we have the path 2, 1 and 0, and this is it. This is the whole solution that we need to take care of, and this is how you would implement a breadth first search for a graph. Same technique is going to be applied for a tree as well. The only difference is that in the tree we don't care about the hash set, because typically you would not encounter inside the infinite loops. But the thing is, inside the tree, depending on the question, sometimes you might have to use hash set, but in the graph you will have to use it. This is a must for a graph. For a tree, this is optional, so take care of this one. Now let's see the first example. And the first example is that we will try to find the shortest path between any two nodes. Now notice that we are given an undirected and unweighted graph in this example, and we are going to use the same example. Suppose we are told that find the shortest distance between 2 and 5 node. Okay, so we need to find the shortest distance between node 2 and node 5. So the quickest way to do it is that we already know that breadth first search is a great way to find the distance, to iterate over the given graph. Also, breadth first search can be a great way to find the path between any two nodes. And how it is able to achieve it is that we are going to start iterating from 2, and we will try to see that whether we can go in any direction that leads us to the value that ends up at value number 5. And if it can, we are going to mark that path, and we will try to see that whether there exists any alternate path that provides us the better answer. If there does not exist the alternate path, we are going to mark this path as the most optimal path and return that as the answer. So let's try to see how we are going to able to be solve it. We already know how to apply BFS using a queue. So awesome, we are going to use a queue. At the same time, we are also going to use a hash set to mark all the visited nodes. Starting from 2, we are okay, so we add value 2 over here. Again, neighbors 1, 0 and 4. So again, add all the neighbors 1, 0 and 4. Now 5 is still not found, so keep going, pop out 2, and then again repeat the same process. So for 1 and 0, it would not lead us to any answer, so again we would eventually pop them out. 4 is the immediate neighbor, and again we would pop 4 out. From 4, we would be able to go to value number 3 and 6. 6 is not going to lead us anywhere, but this 3 is going to lead us to value number 5. And we at the same time are going to plot the path. So from 2, we had we have 3 possibilities. First possibility is value number 1, second one was 0, and third one was 4. Again, from 4, we had 2 possibility. 4 had the value as 6 and 3. And from this 3, we had the possibility of value number 5. I'm just explaining this tree from this graph just for pictorial representation. Don't think that we are going to create a new tree like that, but I'm just showing you that how different paths are being navigated using breadth first search. And the moment we identify the value number 5, we can actually have a function that tracks the previous neighbor from where 5 got it, and then we can keep track of, and we can actually plot a path. So in this case, the path we are going to choose is going to be 2 to 4, then 4 to 3 and 3 to 5. Let's see in our example, the path is going to be 2 to 4, 4 to 3 and 3 to 5, and this is going to be the shortest path between two nodes. Say for an example, if it happens that there exists another path as well, and suppose that path is that even from this 6 we have say for an example one more node, let's just say 7, and then this 7 is also pointing towards 5. Now what would happen is that there are 2 paths that exist that leads us from value number 2 to value number 5. First path is that 2, 4, 3 and 5. Second path is 2, 4, 6, 7 and 5. But in both the cases, we need to find the shortest path, and that is quite simple to find. We would only check that how many number of neighbor jumps or hops we need to take in order to reach from value number 2 to value number 5, and this would allow us the shortest path. Now let me get back to the original topic when I mentioned that the breadth first search is so popular and why it is used in so many bunch of different companies. Because what you did right now is actually one of the use cases that typically Google Maps does it for you. So see, in Google Maps, typically it will you would give it 2 points, and the Google Maps would be able to find the distance between those 2 points. The problem is called number of connected components in an undirected graph. And if we see some of the popular companies who have already asked this question, there are companies like TikTok, Amazon, Google, Facebook, LinkedIn, Microsoft, DoorDash and Twitter. So this problem has been really popular amongst topmost companies, and let's see that what the problem statement is trying to convey. Basically, this is a LeetCode medium problem and also very well-liked problem. It says that we have a graph of n nodes that we are already given, and we are basically given the edges that defines that there is a connection existing between those two nodes for any given graph. Now, based on that, we need to indicate that how many number of connected components are present inside the graph. So let's try to understand this with an example. In this case, currently we have 5 nodes. So basically we are given an n is equal to 5 as the number that defines that there are 5 nodes. We are also given these edges. So we would have given 3 entries, and the first entry is going to be 1 to 2, second entry is going to be 1 to 3, and third entry is going to be 4 to 5. Now based on these two items, we need to define that how many number of connected components that exist, which in this case we can see that this is the first connected component because these 3 nodes are connected with each other, and same way this is the second connected components. So in this example, for this given input, we can define that there exist 2 connected components and we need to return 2 as the answer. So this is the whole ask of the problem. Let's try to understand this with one more example. Suppose in this case, currently we are given n is equal to 7 and we are given all of these different edges. Now in this example, we can clearly see that there exist 4 different connected components, and those 4 components are these, that this is the first one, this is the second one, this is the third one, and though this 7 is not connected with any other node, still this is a connected component in itself because it's connected with itself. So in this case, in total, since we have 4 connected components, we need to return 4 as the answer. Now let's see that what is going to be the strategy to solve this problem. Suppose we take the same example as the input and we will try to see that what should be the answer. Now again, remember, we are given 2 things. First, we are given n is equal to 7, so that we know for sure there exist 7 nodes, and we are given all of these 5 edges. Now based on these number of nodes and edges, we can clearly do one simple thing, and that is to treat this as a graph problem, because that what it is. Basically we know that a graph is comprised of 2 items. First one is a node and second one is an edge, and which we are just told in plain English that these are the 2 entities we are given, so we are going to treat this one as a graph. Now the aim is to find connected components, which means from any single edge or any single node, we will need to define that how many other nodes that particular node is connected with. And if we keep on repeating the same process, and the moment we find the connected nodes, we can eliminate all of those nodes, so and repeat the process for all the 7 nodes that are given, we would be able to find the number of connected components quite easily. And the technique we are going to use over here is the one of the most popular technique in the entire coding industry, and that is called breadth first search. And how we are going to use BFS? Well, we already know that in order to use BFS, we will have to use Q, and we will also have to use number of visited nodes that we have already visited. So using these 2 items, we are going to make our lives so much easier, and let me just walk you through the solution. First thing we are going to do is we are going to we can start from any node, because this is a graph. There is no particular definition that we need to start from here or we need to start from here. Say for simplicity, we start from this node number 0. So we are going to have our queue. Now inside our queue, currently we don't have any elements, and we also have our visited hash set. We can also use visited array. I'm just giving you example of visited hash set. Either way, we are going to have a mechanism to keep track of all the numbers or all the nodes that we have visited so far. So this is our visited hash set, and this one is our queue. Okay. Now first we start with node number 0. Now for node number 0, we are going to mark this one as 0. So we are going to enqueue with 0. Now we are also going to mark 0 as visited. Okay. And we are also going to have one more number that is called the number of connected components. So let me just mark this one as counter. Okay. And currently the initial counter value is going to be 0. But since we found one node, we know for sure that there exists at least one connected component, because it could be connected to itself. So in that case, we are going to increase the number by 1. Okay. Now for this particular 0, we are going to run BFS, And by running BFS, what we would be able to do is that we would be able to go through all the neighbors that this 0 is connected with and then mark all of them in the visited hash set. So even in the future for this n is equal to 7, if we come back to the same node, if that node has already been visited, we will just simply skip over it. So let's just do that. Now for this 0, it has two neighbors. First neighbor is neighbor 2 and neighbor 1. Currently both are not visited, so let's just add entry 0, 1 and 2 over here, and then we will mark 1 and 2 inside our queue because we need to do something with that. Currently the count is still going to be 1 because all the nodes are connected. Now we pop 0 out and we do the same process with 1. Currently for the value number 1, 1 is also visited. So since 1 is already been visited, we do not need to do anything with 1 and we can simply pop that one out. Again 2 is also visited, so we do not need to do anything and we can pop it out. Now after iterating or after doing the BFS starting with the node 0, we have simply eliminated node 2, node 1 and node 0 by itself, and so far the count has been 1 and we have all of these 3 nodes in our visited hash set. But we know that there are still 7 nodes that we have to take care of, so we are going to iteratively go over every single one of them. Initially we started with 0, so we got rid of it. Let's just start with 1. Again for 1, since 1 has already been visited, we do not need to increase the counter and move on to the next value. Again 2 has also been visited, so we do not need to increase the counter and move on to the next value. So all of this entire connected component has been taken care of. Moving on to the next value, starting at position number 3. Since 3 has not been visited, adding 3 over here, adding 3 in the queue as well, going through all the neighbors of 3. Currently 3 only has one neighbor and that is value number 5. 5 is not being visited, and also since we find a new element 3, I forgot to add the increment the count. So now the number of connected components we have found so far is going to be 2. I forgot that, but this is important. Now going back, the currently 3 is connected with 5. 5 has not been visited, marking 5 as visited, at the same time adding 5 inside our queue to visit further neighbors of 5. Now 3 does not have any more neighbors, which means we can get 3 out or dequeue 3, and then we are going to have value number 5 remaining. 5 has one neighbor, that is 3, but since 3 has already been visited, we cannot do anything with that, so we are also going to get rid of 5, and 5 has also been taken out. This means that currently we do not have any elements inside our BFS function. Now moving on, currently we went through 0, 1, 2 and 3. Now we need to go through value number 4 because there are 7 elements inside our given input. For even again repeating the same process for value number 4, currently 4 has not been visited, so we will mark value number 4 as visited. At the same time, we are going to put 4 inside our queue. We are going to go through the neighbor of 4 current, and we are also going to increase the count. I always forget to increase the count, which is the most popular thing which is the most important thing asked in this problem. But anyways, now going back for value number 6, it has not been visited, so we are going to add value number 6 over here. At the same time, add value number 6 over here. Now we iterated over all the neighbors of 4, so we are going to dequeue 4. After dequeuing, currently there is only element number 6 staying in. 6 currently has one neighbor, that is value number 4, but since 4 has already been visited, we do not need to add it to our queue, and then eventually we would pop out 6 as well. Now what we have done is that currently, in order to find these 3 connected components, we already visited nodes 0, 1, 2, 3, 4, 5 and 6, and all of these nodes are visited. Now in the end, we are going to be at the position number 7. Since for position number 7, this node has not been visited, which means we need to increase the counter. So currently the counter is going to be of value number 4. Now we are going to add 7 to our list of visited nodes, and also we are going to mark 7 inside our queue. Since 7 does not have any neighbors, which means we can pop 7 out immediately, and now our queue is empty. We have already iterated over all the number of 7 nodes that were given as the input, and we are basically done with the problem. So in the end, whatever the value that has been stored inside this count variable is the answer we need to return. So simply at the end, we can return that there are 4 connected components in this problem, and this is the complete solution. Now, if you see how beautifully we were able to come up with the solution, and in this case, if you see time and space complexity, the time complexity is going to be big O of V plus E, where V defines the vertices or nodes, and the E defines edges, because that is the time complexity to run the BFS function and go over the entire given input array. So this time complexity is pretty good. If we see space complexity, now space complexity is also going to be big O of V, because we are using the additional data structure of Q and also a hash set or a array. There are two ways to do it. I typically like to use hash set, but you can also use an array as well. Both would work equally fine. In either case, this is a very good time and space complexity. And remember, one of the most important concept is inside the graph theory, the breadth first search allowed us to solve this problem smoothly in a beautiful manner. Here is the coding solution for number of connected components in an undirected graph, where first of all we are given in the input the value n, and we are also given a 2 by 2 array called edges. So first thing we are going to do is create an adjacency list and to create a graph like structure. So this is going to allow us to iterate over graph in a much easier fashion, which this process is doing, where we are running across every single edge and every single node and plotting them on the graph. After that, we are going to have our boolean array called visited, and we are also going to have a value called count that initially we are going to set it up as 0. We are going to run our for loop starting from value 0 to the total number of n that is given in the input. And then inside the for loop, first thing we are going to check is that the current ith position, if that is not visited, then we are going to call our BFS function, and at the same time we are going to note it as the new connected component found, and we are going to increment the number of count. Now let's see that what is going to happen in our helper method BFS, where we are taking a graph as the input. We are also taking the number of nodes that have been visited so far, and we are also using the starting pointer from which we are entering inside this given graph. So first of all, we are going to initialize our cube. We are also going to have a visited array that we are going to mark as true for the current node that we are visited. And while there are no entries inside the cube, first of all, we are going to pop the last added element inside the cube, visit every single neighbor of that node, and for all the neighbors that has not been visited, we are going to mark them as visited, and we are going to add it to our existing queue. And by doing this operation, we would be simply running through every single connected component. So suppose here I give you like 0 as the input, then through this BFS method, 0, 1 and 2, all three nodes would be marked visited because they all are connected. And this is what this operation is doing. And in the end, after this for loop ends in our main method, we simply need to return the count that we have found that would allow us to find the number of connected components. Let's try to run this code. And our solution works perfectly fine. Let's submit the code. And our code runs decently efficiently. And don't worry about that you are not being able to see the code. I'm going to put this code inside the GitHub, so you would be able to find it quite easily from there. So the Leetcode problem we are going to explain is going to be binary tree zigzag level order traversal. This is a really popular problem, and this has been asked in some of the top tier companies such as Amazon, Bloomberg, Microsoft, Facebook, Apple, LinkedIn, Google, Samsung, Goldman Sachs, and TikTok. So that is why I'm paying my utmost attention. I highly urge you to pay your attention for this problem as well. If we see that this is a Leetcode medium problem and also very well liked problem. Now in this problem, we are given the root of a binary tree, which means a binary tree means that any single parent can have at most 2 children, nothing more than that. So now we have the root of this binary tree, and now we need to return the zigzag level order traversal from its nodes values. So what does a zigzag level order traversal means? So first of all, before understanding the zigzag level order traversal, let's understand what does a level order traversal means. Level order traversal simply means that first we go through the first level, that is level 0, then level 1, then level 2. So if we see the level order traversal, first we would it go through value number 3, then second level, so that is value number 9 and 20, and then the third level, that is 15 and 7. But since in this case the level order traversal that we were making was pretty simple, we were going from left to right. So we went from here, we went to left to right, again from here we went from left to right. But in this case we are making our lives easier and we are going in the zigzag fashion, because that is the current trend. And zigzag fashion is that first we start over here from left to right from the root node, then we go in the zigzag fashion. So we go like this, and now again we repeat the zigzag pattern, and now we go from left to right again. So for one level we go from left to right, next level we go from right to left, and again next level we go from left to right, and we keep on repeating the same process. So in this example, if you see, first we went through level 3 left to right, this was the value. Second we went through the right to left, so 20 and 9. So from after 3 we visited 20 and 9, and then we went through 15 and 7, 15 and 7. And let's see what would be the solution for this problem. Okay, suppose this is the input we are given. Now first let's see what is the level order traversal going to be. First we are going to visit value number 1, then we are going to visit in this fashion, so the value is going to be 3 and 2, then again from this fashion, so value is going to be 4, 5, 6, and then again from this fashion, so the 8 and 7. This is going to be the answer for sure, we already know that. But how we are going to come up with the answer? In order to come up with the zigzag level, first we need to go through the simple level. How to go through simple level order traversal? Well, for what we are doing in a simple level order traversal is that we are iterating the parent, then we are iterating its child before iterating its grandchild. So in this case, first we are going to we are at this place, we are going to iterate over its child. After iterating both children, we are going to iterate its grandchildren or the children of these children. So first we would be covering this level, then after covering this level we would be going through the children of these nodes, and so going in this fashion, and again repeating the same process with this one. And this can be achieved using breadth first search because it's pretty simple to do, and this is how how traversal is done in trees using breadth first search. That is a level order traversal. So even in this case we are going to use the breadth first search to run in a simple level. But how do we use breadth first search? Well, from our experience we know that in order to use breadth first search we need two items. We need a queue and we need a visited hash set. But the thing is, we only need visited hash set in a graph kind of a problem where there is an issue of us running in an infinite loop. There is no issue of us running in an infinite loop inside a tree, so we are not concerned about using a graph. In this case we are only going to use a queue. And currently I'm just showing you how to do a level order traversal, and then we will do zigzag level order traversal. So first let's just see the level order traversal. For that we are first of all going to start at the root position and we are going to populate that value inside our queue. So this is currently value number 1. Now we are going to visit the children of 1 before visiting the grandchildren of 1. This is the whole logic of the BFS, that we are going to visit the children before visiting the grandchildren. So who are the children? Obviously 2 and 3. Again we are going to add values 2 and 3 here because it has 2 children and we are going to mark them. Now we visited all the children of value number 1, so we are going to pop value number 1 out and we are going to put it in the answer, that we traversed this part already and now we only have values 2 and 3 inside the input. Now again for 2 and 3, 2 has children that we haven't iterated over. So who are the children of 2? 4 and 5, mark them here, and same way get rid of 2. So 2 has been taken out, and now currently the entries are 3, 4 and 5 inside our queue. 3, 4 and 5. Again 3 can be kicked out by adding 6 at the end of the queue. We added 6 at the end of the queue. Awesome. Now 3 is also out. Currently the entries are 4, 5 and 6. Now even for the values 4, 5 and 6, starting at position number 4, it does not have any child, so 4 can be kicked out without any repercussion. 5 currently has a child 7, so adding 7 at the end and getting rid of 5. So we can put 5 over here Again, values are 6 and 7 in place. Again, for value number 6, it has a child called 8, adding 8 in the end and getting rid of 6. And now after that, there are only two values left, 7 and 8. Currently 7 does not have a child, so we can get 7 out. And also 8 does not have a child, so we can also get 8 out. And this would be the solution. But in this problem, what we did is we went in the normal level order traversal, not the zigzag level order traversal. So let's see how can we make zigzag level order traversal possible. Currently, what the concept we are using inside the queue is, currently we are using the first in, first out principle that gave us the level order traversal. But what happens is that when we move from left to right, this concept is absolutely true, that we can get we can have like first in first out, and that would give us the proper level order traversal. But when it comes to reversing, imagine that in this case, rather than getting 2, since 2 was already inside the loop before value number 3, if we pop 3 out before 2, then we would have been able to accomplish our mission. So since in this case we are going in the zigzag fashion, remember zigzag fashion is going to be like this, where and on one iteration we are moving from left to right, next iteration we are moving from right to left, and again for the next iteration we would move from left to right, and we would keep on repeating in the alternate fashion till we reach to the or to all the nodes inside the given input. So now let's see that what are some of the adjustments we can make to make our lives so much more easier and fix this issue that we were having in the level order traversal. The solution is quite simple, and the solution is that whenever we have to find from left to right, we can use the concept of first in first out. So this first in first out is going to use on these two occasions. But when we need to move in the reverse order or right to left, in this case we will have to use the concept of last in first out, because logically what was happening in this case is that logically we were traversing in left to right for every single one of them in the level order traversal. So typically we were going like 2 and 3, but imagine since 3 was last added, if we took the last in first to approach, then inside the solution we would have values such as this one. So 1 is following FIFO, first in first out. So 1 was added first and 1 was removed first. But for this particular position, we are using the concept of last in first out. So even though 2 was in the queue before value number 3, we are going to have 3, that was the last value, come out before the value of 2. So 1, 3 and 2, such like this. Again we are going to use first in first out for this particular level. So the solution is going to be 4, 5, 6. That is pretty simple. But for these two, again we are going to use LIFO principle, and that is going to give us the answer of 8 and 7. Now if we see this sequence 1, 3, 2, 4, 5, 6, 8, 7, this matches with the original answer we wrote at the beginning, 1, 3, 2, 4, 5, 6, 8, 7, and this is the whole solution. So let me clean this up a bit, walk you through my solution, where we are simply arranging the way we are entering the values inside the inside the queue and popping the value out of the queue. Okay, so now we are going to have our queue. We are going to add all the entries, and the only simple thing we are going to do is whenever we have to move from right to left, we are going to pop the value at the from the end of the queue rather than popping from the beginning of the queue, because we are flipping between FIFO and LIFO principle. And the one data structure that is capable to do this is actually a DQ data structure in like both Java and Python languages. So you can use either one of them. Okay, so let's start iterating, starting from value number 1. 1 is placed here. Currently 1 has 2 child, 2 and 3. So we are going to mark 2 and 3 in this position. Currently for 1 we are iterating from left to right. So we are going to get the last in first out. So 1 would come out. Now the values are located as 2 and 3. Even for 2 and 3, currently we need to get them out in the zigzag fashion or right to left fashion. So for that, first we are going to pop it from the end. But before popping it from the end, we will first add the children of 2 and 3. So the child of 2 is 4 5, so let's add 4 5 here, and child of 3 is 6, let's add 6 here. After doing that, we are going to pop 3 out first, and then we are going to pop 2 out first. So 3 and 2 has been out because 3 was value before 2. And again, for 4 5 6, we need to do the same thing, but we need to do in the left to right fashion. So 4 5 6 are going to come out as themselves, but before that we are going to iterate through it their children. So 4 currently does not have a child, so we can pop it out without any repercussion. But 5 has a child, the value is 7, and 6 has a child, the value is 8. Again we pop 5 out, so popping 5 out should be simple, and popping 6 out should be simple as well, because we already took care of them. But for value 7 and 8, again we are moving in the right to left direction, so last in value 8 is going to come out first before 7 coming out, and in the end we would not have any values inside our queue, which means we can get rid of it. And now you see the traversal is being done in the level order and also in the zigzag fashion, and that is the most important fact, and this is how you solve this problem. Again, if we try to see the time and space complexity, the time complexity is going to be big O of v plus e, or vertices plus edges, or nodes plus edges, because we are using our BFS. And space complexity, since in order to use the BFS we will have to use a queue, the space complexity is going to be big O of v, or the number of nodes or number of vertices inside our given tree. And this is the whole solution. Let's see the coding solution for binary tree zigzag level order traversal. So first of all, for this one, we are given the method that to return a list of lists that contains the zigzag level order traversal of the given input tree, and as an input we are given the root node. So first of all, we are going to check for the edge case, that if the given root node is null, we can return an empty new array list immediately. If that is not the case, first we are going to initialize the array list. Inside this array list, first for the first node, we are going to add the root node, and we are going to add a null node as well, and we are also going to use a new tree node linked list to iterate over the given input tree. Now we are going to mark the level list, because every single level is going to contain a different set of answers, and we are going to use this boolean parameter to keep track that whether we need to traverse from left to right or right to left. So is order left is initially set to true, which means currently at the beginning we are moving from left to right. Now inside the while loop we are going to do our BFS function, where if this given boolean is order left is true, which means we are going to use the last in first out and add all the elements inside the level. If that is not the case, then we are going to use the first in first out and also add all the values that are present on that particular level. After adding all the levels, we are simply going to populate our result list based on the level list we have created, and then we are going to initialize a new level list for the next level, and again we are going to change the ordering from left to right to left for the next level. And after repeating the same process again, even for the next level, the ordering is going to be again left to right. In the end, after this BFS operation doing loop ends, we would have our result linked list populated, and we would be able to return that as the answer. So let's try to run the code. Seems like our solution is working as expected. Let's submit the code. And our code runs pretty efficiently compared to a lot of other solutions. And don't worry, I'm going to post the solution of this code inside my GitHub repository that is open to public, so everyone would be able to see that. So the question is number of provinces. This is a Leetcode 547 problem, and this problem has been popular amongst top tier companies. So companies such as Amazon, Bloomberg, Apple, Two Sigma, DoorDash, Goldman Sachs, Google, Uber, they have all asked this problem. So that's why I hope that you pay enough attention to this one. If we see the problem statement defines that there are n cities that we are given, and we are told that some of these cities are connected, some of these cities are not connected. Now if say city A is connected with city B, and city B is directly connected with city C, then city A is indirectly connected with city C. So A is connected with B is connected with C. Suppose this is the relationship, then we can define that A is also connected with C. This is what this problem is, the statement is referring to. Now going back, we are given the definition that what a province is. A province is a group of directly or indirectly connected cities and no other cities outside of this group. So suppose we are given cities like A, B, C, D, something like this. And we are given that A is connected with B, B is connected with C, and we can also refer that indirectly A is connected with C as well. Currently this D is not connected with anyone. In this case, we can define that this A, B, C makes a province, and this D by itself, currently since it is not connected, it is not making a province. But suppose we identify that another city E that exists, that is connected with city D, then we can define this to be the second province as well. Okay, so now we know that what the problem statement has given us. We are given n cities and we are given the connection between those cities, and we are also given the definition of what a province is. Now we are given an n cross n matrix, and wherever there is a connection between any two entities, that particular value has been marked as 1. That defines that the ith city and jth city is connected. And if the value is not 1, if the value is 0, which means that those values are not connected. Now based on this given input, we need to define the total number of provinces. This problem is very similar to one of the previous problems we solved, and that is the number of connected components. And how? Let me just quickly show it to you. What we are given is that we are told that we are given a matrix, and inside the matrix, using the values 0 and 1, we are going to define that whether any two values are connected or not. Okay, so suppose the values are A, B, C, D, and here A, B, C, D. Okay, all the values are by default going to be connected with each other, so I'm going to mark it as 1. Suppose, let's just take the same example. So these are all the items we are given. This is true. Based on all of these items, what we are given is that this is actually not a matrix, but actually this is an adjacency matrix. And adjacency matrix is one more way to represent a graph. Since this is one more way to represent a graph, we can, rather than considering these as cities and these are connection between them, let's just try to think of these as nodes and edges, where nodes are the cities and edges are the connection between them. And now this becomes a very simple problem that we can solve using BFS quite easily. And the whole problem statement now becomes is that we need to identify that how many number of connected component exist inside any given graph, and those connected components, we need to return them as the answer. So I have already solved this one in past, but I'm going to quickly show you the solution again. And simply we are going to use breadth first search. For breadth first search, we all know we need two items. First one we need is a queue, and we need some way to keep track of all the visited nodes so far. So let's just do that. I'm going to initialize our queue, and also I'm going to initialize our hash set that is going to keep track of the visited hash set. Okay, so this one is for visited and this one is queue. Now we can start at any given node. So suppose this is the input we are given. Currently nodes are 1, 2, 3. These three cities are connected, and city 4 and 5 is connected. We are also going to mark one more variable called provinces, and initially the value of the provinces is going to be 0. Okay, so currently this is the variable that is going to keep track of the number of provinces we have been able to find so far. Currently the value is 0. Now let's just pick any arbitrary value. So we start with node 1. So let's just run a BFS starting with node number 1. So first we are going to, since 1 has not been visited, we are going to mark as visited because we are visiting it. We are going to add 1 inside our queue. Now the moment we find a value inside a queue, we are going to iterate through its neighbors. Currently 1 has two neighbors, value 2 and value 3. Both value 2 and value 3 are not visited, so we are going to mark them to the number of visited nodes, and we are going to mark 2 and 3 here. Now we iterated over all the neighbors of 1, so we are going to dequeue 1 out, and we are going to remove it from the queue. Now currently we only have values 2 and 3. For value 2, the number of node is 1 and 3 as its neighbor. Both 1 and 3 have been visited. So since they are visited, we are not going to revisit them, and we are going to pop 2 out as well, that stating that we visited all the nodes of 2. And at the same time, we are going to pop 3 out as well, since the neighbors of 3, 1 and 2 are already been visited. Also, I forgot one key important thing, and that is that the moment initially when we started iterating through 1 and we found that 1 has a neighbor 2, immediately we needed to add the number of provinces to 1, because we found at least one province. So we would have found one province, and in order to finding that province, we already visited all 3 nodes. So we are going to mark these 3 nodes as visited. Now, since in the input we are already given n is equal to 5, we initially started with n is equal to value number 1 because it was not visited. Now we will start with n is equal to 2, but that has also been visited, so we will simply skip over. N is equal to 3 has also been visited, so we will simply skip over. Last value is n is equal to 4. N is equal to 4 has not been visited, so marking 4 to our visited list, adding 4 to our queue, and now 4 has a neighbor 5. So again, the moment we find a neighbor, we are going to increase the number of provinces to 2. We are going to add 5 to our visited list. We are going to add 5 to our queue, and then we are going to pop 4 out because we visited all the neighbors of 4. But we haven't visited all the neighbors of 5. Currently for 5, since 5 has already been visited, we do not care, but 5's neighbor 4 has also been visited, which means 5, we also visited all the neighbors of 5. So now we get rid of 5. Now initially for this n is equal to 5, we had gone through 1 to 4. For the 5th value, 5 is also present inside the number of visited list. So we can define that 5 has also been visited, and because of that, we went through all the nodes or all the cities that we were given, and the number of provinces that we were able to make was 2, and which we are going to return as the answer. If we see solution for the time and space solution for this one, basically the time complexity is going to be big O of V plus E, where V is the number of vertices or number of cities in this case, and E is the number of edges or the connection between the cities that we are given. Pretty simple, and this is pretty standard. Space complexity also going to be big O of V, because the space complexity is based on the visited hash set and the queue that we have to generate, which can hold maximum up to 5 cities for this example. So it is directly related to the number of vertices that is present inside our given example. Awesome. So see how knowing BFS made our life so much easier. Let's move on to the coding explanation for this problem. Let's see the coding solution for the number of provinces problem. This is a really unique problem, and the solution is actually quite simple. First of all, in the main method, we are given the 2 by 2 matrix that defines that what are the number of connected components. Based on that, we would be able to easily identify that what is the total number of edges or total number of nodes present. And once having that, we are going to initialize our visited Boolean array, and initially the number of provinces is going to be 0. Now we are going to run our for loop, where we are going to call the BFS method. Inside the BFS method, first of all, we are going to check that whether the current node has been visited or not. If the node has not been visited, we are going to call BFS method to visit all the connected components or all the cities that are connected with each other that form a province. And we are going to increase the number of provinces. So we are going to do provinces plus plus, that was initially set it up as 0. Now let's see that what is going to happen inside our BFS helper method. The answer is quite simple. In the BFS, we are going to initialize our queue, and we are going to have a visited array that to keep track of all the nodes that we have visited so far. For any single input that we are given, we are going to keep on iterating all the neighbors of that particular node that it is currently connected to, and we are going to mark all of them visited. So even when we encounter the same city that has already been processed, we do not reprocess it again because it has already been marked visited. And after this entire process ends, currently in this loop, this provinces variable should have all the answers populated. We can simply add them over here and return provinces as the answer. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 99.26% faster. So this is pretty fast solution. And don't worry about this. I'm going to paste the solution inside my GitHub, and the link is in the description, so you can check it out from there.